SwayamPrabha. Digital India. Educated India.
Hello and welcome everyone to today's lecture for this series on the modeling of multiphysics system. So today's lecture is the second in the series of the solid mechanics lectures that we are doing. So in this segment, in the last lecture, we had talked about strains, and we have seen how a solid mechanics problem is set up. We are doing single physics in these segments of modules. Eventually we will go to coupled physics. We have seen the first step was to understand the relation between strain and displacement. So any solid mechanics problem, any deformation, you would first find what is measurable and what is not measurable. So the measurable quantities are typically your deformations or displacements. So a body being elongated or twisted or moved or rotated, something that you can physically measure, that's tangible. That's one. Second thing that you can measure is the surface forces or the body forces that is acting on the body. So a body can be pulled by some force, it can be compressed, it can be twisted, it might be under some action of gravity, that's why it's getting pulled downwards, etc. So all of these components can be measured physically, and there are instruments that can detect them. So that is the concept of most of our modeling cases, is to understand which variables are measurable, which variables that you can realize, and once we have those variables, then we try to develop governing equation and try to estimate other values or other variables which cannot be tangibly measured. For example, stress is the resistance to internal deformation, is something that you cannot measure. Right. It is, however, necessary to know the stress state of a body, because using the stress state we can find out the conditions of failure, and we need to design a system that will avoid failure. So that is the objective of solid mechanics. We have seen in the last lecture that there are around 4 to 5 steps to go to it. So the first step we have covered was to understand the relation between deformation and strain. In the next 2 steps, we will talk about forces and stresses and how the forces lead to the force equilibrium or the stress equilibrium equation. Right, so we will find a relation between the applied force on a given area leading to traction, how is traction related to stress, how the net stress on a body using the Newton's second law can give us acceleration or the deformation. Right, that will be the basis for this lecture. In the upcoming lectures, we will find out the relation between the displacement or deformation with the stress, that is the constitutive law, and then we will put everything together in our last step, and that will be to find out the net equation, that's the Navier's equation, one equation based purely upon displacement with the boundary conditions which can be both driven by displacement and stresses. So stresses or forces at the surface can be measured, but in the bulk we cannot. Right, so we will develop an equation which will be driven only by the displacement, will not have any force term eventually. However, at the boundaries we can have forces. So displacement related to forces. All right, so we have seen what was strain and what was deformation. We have seen different types of strains, some in which the strain was related to the initial coordinate system, some in which the strain was related to the final coordinate system. We had looked at Lagrange strain and Euler strain based upon the frame of reference. We have also looked up for on our infinitesimal strain and the infinitesimal rotation, in which the second order, the higher order terms can be made 0. In this case, del u by del x, or our deformation gradient, our displacement gradient is very small. So in this case, we can assume that our strain is small strain, and we have seen that the strain tensor is symmetric and the rotation tensor is q symmetric. Okay. With those definitions in mind, we will have other definitions of strain as well based upon the type of application. Just like strain, we also have different types of forces and different definitions of stress. It doesn't mean that the stress is different in a body, it is just the perspective in which we are looking at. Again, keep in mind, deformation of the body is absolute. Strain is a term relatively defined. Likewise, forces acting on a body is absolute, and the stress definition is relative to the perspective or the frame of reference that we are talking about. Okay, with that definition in mind, let's hop into this lecture. So we will talk about the types of forces. So if we draw a coordinate system, and this is our initial body, right, and this gets deformed. So, this deformed body, this is our initial frame of reference, has a surface S or a surface A and some volume V. This gets deformed by some internal body force B vector and some external surface forces. So, we can have shear, we can have axial stresses, all of this is given by some stress vector on the surface. So, this is our surface again, dV is equals to A. Okay. Now, let us define there are two types of forces that can exist. So, number one is called our surface force. These act on the boundary or surface of a body, and say example of it could be one small example could be like a pressure force or hydrostatic stress. You can also have shear stress. These are all surface forces or surface driven effects. Then we can have body force. So, body forces, so these act in the bulk or volume of the body. An example for these will be gravitational forces, or electromagnetic forces. Okay. So, surface forces, so this pen dropping on my hand, it is driven by gravity. The force acting on it that's pulling it down will be the gravitational force. If it is just resting on my hand, then the gravity is pushing it down, and the hand is giving a resistance for the body to stay in the place. However, there will be some deformation to counter this. If we have instead we have surface forces, then me pulling this pen or pushing this pen or rotating this pen, these are the surface forces because they are acting on the surface of the body. Alright, so let us define a vector which is called the traction vector. So, the traction vector T vector is defined that limit for the area tending to 0, the applied load divided by the area is our traction vector. Okay. So, in this case our load therefore is equals to integral of the traction vector into dA over this area A. So, what is a traction vector? Traction vector is, in a very crude or rudimentary definition, is force per unit area. Okay, so this is what you would usually call stress in a UG level course or in your high school when you have studied solid mechanics or stress strain relations. Then the typical definition of stress was force per unit area. That was the case of a longitudinal body being elongated, if you remember, right, a body being elongated and stretched, then the load being applied on the cross section area of the body, that's what we called stress, right. That is not the definition of stress, that is actually the traction vector on the surface. Stress has 9 components, a vector has 3 components in a 3D coordinate system. Alright, so this is our traction vector and the load that we are getting is a surface force. Okay. Then our traction vector can have normal and tangential component. So, the normal and tangential components of T vector will be T vector of n will be T vector dot with the surface normal into n vector, and the tangential component of T vector will be T vector minus the normal component. Okay, so the traction vector dotted with the surface normal, so it will give you the imprint or the shadow of the tangent vector of this traction vector on the normal direction. So that it is a cos theta, along the direction of the normal will be the normal component, and the other component will be our automatically will become our tangential component, right. So let's draw a diagram just to visualize this. This is a surface, this is our surface normal, this is our traction vector t, then along this direction will be our Tn, and along the surface in this direction will be our Tt. Okay. All right. Then the next type of force is our body force. So the body force or the body stress and can be defined by B vector. So 1 by rho, limit the volume tending to 0, dV tends to 0, dP by dV. Okay. Or P vector is equals to integral of rho B vector to dV. So in this case B vector, so this is our body force, and B vector is a specific body force. Acting on the body. Specific means per unit weight, right. So force per unit weight. So if you see in this case, force per unit weight into density will be force per unit volume, into the volume will give us the force. All right. So the total force acting on the body will be a superposition of surface and body forces. Okay. So our net P vector therefore will be integral over the surface, our T vector along the normal into dA plus the body force rho B vector integrate over dV. This is our net force, and we will come back to this equation when we will look at the conservation of linear momentum and our governing equation. But so far, just to realize that we have a traction vector, that is force per unit area on a given surface. It can be any surface. It can be this curved surface at the end, this top cylindrical surface. We can make a intersection at a plane, and on that plane we can find the traction. Any surface, any exposed surface, we can find out the traction, and the traction multiplied with the area will be our surface force. Our body force into the density of the body multiplied or integrated over the volume will be our body force. Summation of the two forces will give us a net force. Okay. Now let's go into what is a stress tensor. In definition, what is stress? So let's first define stress. So stress is the resistance by a body against deformation. Okay, this is an extremely important definition and something that completely deviates from our earlier understanding of stress. Stress is not force per unit area. Force per unit area would be a vector. Stress is not a vector, it's a tensor, right? It has 9 directions. So stress rather is the internal resistance. So let's write the term internal. So it is the internal resistance provided by a body against deformations. If a body wants to deform or wants to go away from its initial state, and there are something that is preventing the body from going into its natural state, then the body is under stress. Okay. So the Cauchy stress tensor is that you consider a solid body under mechanical loading, then our sigma, that is our Cauchy stress tensors Ij is equals to traction vector along J, E cap along I, where E is our surface normal of the plane that we are projecting, and t is our traction vector. Okay, so this is the definition. Sigma ij is a tensor, so it is a tensor quantity. We can relate our traction to our stress as T of I is equals to Nj sigma ij, where n is normal vector and sigma ij is a Cauchy's tensor. Okay. In terms of matrices or in terms of vector notation, T vector is equals to n vector dot with sigma tensor. Okay, n vector dot with sigma tensor. I am sorry, this should be ji, not ij. Okay, so if we look at this I and j component, so I component, it determines the direction of the force, or traction. J determines the direction of the plane. So if we draw a drawing for a 3 coordinate system unit, say this is E1, this is E2, this is E3, and always check for the right hand thumbs rule, right? E1, E2, if you put your hand, your thumb should point towards E3. That is your RHS rule. For the right handed coordinate system, we are using right handed coordinate system for our for all our analysis. We do not use left handed coordinate system in this case. Okay, so this is our E1 plane. Our surface normal is EI or NJ in this case. So E1 is equals to Nj. Our forces on this plane can act on this direction, that can be T1, along T2 and along T3. Okay, so along T3. So we can have T1, T2 and T3. So 3 components of traction on this one E1 plane, and that is why you need a 3 by 3 matrix of stress, so that each component can be mapped along that direction. Okay, so on this plane, E1 plane, so then we can have T1 along this n vector will be equals to T1 along E1 n1 plus T1 along E2, well, n vector is this vector, right. So T1, T2, T3 on this plane, that is what we are looking at. So let us write in terms of a matrix Ti of n vector is equals to sigma 1j n sigma 1 I, I am sorry, not j, n1 plus sigma 2 I n2 plus sigma 3I and 3, okay, along these directions, which is equals to sigma j of I and j. So 1, 2, 3 are the directions of the plane or the normal component. So any normal component, when you resolve along all the 3 directions, that will be along all of those 3 directions, and T1, T2, T3, in this case T1, T2, T3 will be the equivalent projections of the vector on those planes, right. So that is how it is written. Okay, does this make sense? Yes, all right. So let us repeat this one more time. So if I write, this is our n vector, so this is n1, n2, n3, this is our sigma vector, sigma 1 1, sigma 1 2, sigma 1 3, sigma 2 1, sigma 2 2, sigma 2 3, sigma 3 1, sigma 3 2, sigma 3 3, and you multiply this n with this sigma, you can find out your t vector along those directions. as a dot product. All right. Now, the Cauchy stress tensor completely characterizes the internal forces acting on a deformed frame of reference, on a deformed body. Okay, this is an important definition. So, the Cauchy stress tensor sigma ij is what you actually call the true stress. So, you have learned what is engineering stress and what is true stress. Our engineering stress is based upon our initial cross section, right? Our true stress is based upon our final cross section. In the same way, our Cauchy stress tensor is a true stress tensor in which the applied force at that time divided by the applied cross section at that time, right? Whatever is a deformed cross section, not the initial cross section or the undeformed cross section, but the final cross section at that point. That is why Cauchy stress tensor is the most used stress tensor, because you are aware of the final state of the body. You do not have to track it back all the way to the initial state and what was the engineering. So, we will talk about other stress definitions as well, in which we will go back or trace back to the original reference point. However, in most practical applications, we are aware of the final state of reference, right? So, whatever is our final state of the body, we are aware of the forces on that body, we are aware of the cross section of that body, and that is why the Cauchy stress tensor is useful. All right. So, if we look at a coordinate solid, say this is our solid, this is our n vector, and this is our t vector along n vector into dA. So, we are finding the projection on this direction, right. We can say this is E1, this is E2 and this is E3. So, along E1 on the negative axis, this is minus E1 cap, our say this is T1 along this minus E1 cap into dA. So, this area let us say is dA1, this total area on the top is say dA. Okay. Likewise, we have dA2 and dA3 based on the perpendicular planes that we are looking at. So, the physical significance that the sigma ij or the Cauchy stress tensor represents the ith component of traction vector, that is T of I, and the jth component of the normal vector, that is E of j or n of j. Okay. It is also called the true stress or force acting on the deformed area or frame of reference. Okay. So, this is the true stress. It is the force acting on the deformed area or the deformed frame of reference, and something that we can tangibly measure, and that is why it is of importance. All right. Apart from this, we will have 3 other definitions of stresses or 3 other stress tensors which come of use. The Cauchy stress tensor is actual force, just as a reminder, per unit actual or deformed area. It is the most physically significant definition of stress. Okay. The other force measures or stress measures regard forces as acting on the undeformed area. Alright. So, how do we come from the deformed to the undeformed area is that we use mapping. We have looked at our displacement gradients and deformation gradients. So, if we can use those displacement and deformation gradients to map our final area to our initial area, so we use mapping. So, we need to map our deformed area to the initial state. Okay. In this case, all our older definitions of deformation gradients will be useful. Okay. So, one thing to remind, so as a reminder, because we will be using these, our deformation gradient Fij was equals to del ij plus del ui by del xj. It was the deformation gradient. And what was it? We remember that y of I was equals to x of I plus u of I, where x was the initial position, u of I is the displacement, y is the final state. Del yi by del xj was equals to del ij plus del ui by del xj. So, the gradient of our final displacement was equals to the displacement gradient. Okay. That is one thing. One more thing is that the Jacobian J is given by the determinant of the F tensor, and this is represents the volumetric changes due to deformation. Okay. With these in mind, we can then start with our three definitions of stress. So, the other three stresses, the first one is called the Kirchhoff stress. It is given by tau is equals to j into sigma ij. The second one is called the nominal stress, also called the Piola-Kirchhoff 1 stress, given by Sij, which is j times f inverse of ik sigma of kj. If you want to write in terms of vectors, this is j into sigma equals to tau. This is S is equals to j into f inverse sigma, and then we have a material stress, which is also called the Piola-Kirchhoff 2 or PK2. Okay, this is PK1, this is PK2 stress, and is defined by this sigma sigma ij is equals to j f inverse of ik sigma kj f inverse of jl sigma kl. My bad. Sigma kl f inverse of jl. So, sigma is equals to j times f inverse sigma f inverse transpose. So, these three are the other three definitions of stress apart from the Cauchy stress. So, we have our Kirchhoff stress, our nominal stress, and our material stress. Okay. The inverse relations are as follows. Sigma ij is to 1 by j f of ik s of kj which is sigma is equals to 1 by j f vector s f tensor s tensor, and then sigma ij is equals to 1 by j f of ik sigma of kl f of kj, which in other terms sigma is equals to 1 by j f transpose. Okay. So, this is how we can move between our Cauchy stress tensor and the other three stress tensors. Kirchhoff stress is not that used or not that commonly used, but the nominal and the material stress tensors can be used in certain applications. Our Cauchy stress tensor and the other three stress tensors. Kirchhoff stress is not that used or not that commonly used, but the nominal and the material stress tensors can be used in certain applications. No physical significance. Okay. Then we will come to our nominal stress tensor. So, our nominal stress tensor can be considered as the internal force per unit undeformed area. Acting within a solid. Okay. So, Cauchy stress was final force by final area or deformed area. This is final force or the actual force, internal forces, divided by the undeformed area, right. So, we need to have a transformation of the final area to our initial area. Let us see what was our Cauchy stress. So, dpi was equals to dA, that is our undeformed deformed area, into nj sigma ji. This is what we have done for the Cauchy stress. Okay. Now, this force remains the same. The area needs to go from A to A naught. So, let us take this as a coordinate system. This body is deformed, and let us say that this is our initial body, this is our deformed body. So, this is the normal n naught, and this is our load dp naught, and this is our deformed n, so our dp vector. This is dA naught and this is dA. Okay. So, dA and dA naught are related, as dA along ni is equals to j f inverse of ki n naught k dA naught. So, that is how you can relate the deformed area to the undeformed area. Ni is a normal component along the deformed direction, n naught is a normal component along the undeformed direction. dA and dA naught are the respective areas. So, we multiply it with j and f inverse of the or the inverse of the displacement gradient. Okay, let us substitute this in our Cauchy stress. We get dp of I. So, we are replacing this dA into nj. So, this will be j f inverse okay. So, we are replacing this term. So, here I is replaced by j, k of I is replaced by j, that is what we did, into sigma of ji. Okay. Now, let us club a few terms together. So, we can say dA naught into n naught k into j f inverse kj sigma ji. This, if you look at the previous definition, fik into kj. So, fkj into ji is equals to dA naught n naught k into s of ki. dp of I. And we have come all the way up to our nominal stress. Definition. Okay, so this is how we can coordinate. We can change our coordinate axis from the perspective of the Cauchy stress, that is final force to deformed area, to the nominal stress, that is final force to the undeformed area. We have just replaced the area term and we have moved all the way over. Okay, one thing to point out in this case that I would maybe should have done earlier is that the Cauchy stress tensor, if we just go back a few steps, the Cauchy stress tensor is symmetric in nature. Okay, so I might flip sigma ji with sigma ij. Please be aware that it is done with the consideration, and that is the case that Cauchy stress tensor is symmetric. So this transpose is gives us the same vector, the same tensor as an output. Okay. The third one is our material stress. So we will just do it quickly. So stress tensor, its physical definition is that it considers the resolved initial force on the undeformed area. So what it does, it also takes a final force to its initial state, what could have been the projected initial force and the initial area, right. So you are taking not only the area to the original format, you are also taking the force to the original format. So if that is the case, let's write it over here. So we can write it over here. Our force transpose, so we are going from dp vector to dp naught vector. So our dpi will be equals to Fij dp naught of j. So if we replace this into our force equation dpi and we replace dA by dA naught and we also replace our dpi with dp naught. So we can write this F of ik into d of p naught of k. This will give us dpi is equals to dA naught into n naught of k or you can use j in this case as well because we have used k already into s ji. Okay, so just make sure that's what I am looking at is I just wanted to make sure that the index are correct. So I is the unrepeating index, k is repeated over here is summed up, j is repeated over here and is summed up. So we have taken the nominal stress definition in here. All right, let's multiply with F inverse ik on both sides. So F inverse of Li into ik d naught pk is equals to dA naught n naught j sji Fli inverse. All right, these two will give us del of Lk d p naught into k is equals to dA naught n naught j, and this term is our sigma of j into L. Now j is repeating, L is the unrepeating index, and we can thus say from here that since delta Lk into dp naught k, L and k can be replaced. So dp naught of L is equals to dA naught into n naught j into sigma jl. All right, this becomes our material stress. So what we did from Cauchy stress tensor definition, that is over here, we converted this dA to dA naught and we got our nominal stress. Now using this nominal stress definition, we converted this dpi into dp naught and dp naught of j, and we took the displacement gradient f from the left hand side to the right hand side by multiplying inverse on both sides, and we came up with the formulation for the material stress. Again, a material stress is symmetric, Cauchy stress is symmetric, our nominal stress is not symmetric. Now, these definitions can be confusing at times. We are looking at different prospects of deformed area, undeformed area, initial stress, force state, final force state. These definitions are important when you are considering bodies with large deformation. See a rubber band, you are pulling it and you are stretching it to long distances, or there is a viscoelastic solid. In those cases where there is large deformation, you would definitely need to consider these different definition of stress. But for most engineering applications where you are doing modeling, the deformation scales are very small. Right? The strains are infinitesimal, in the range of less than 10%, so less than 0.1. So it can be 0.08, 0.05, 0.01. In the case of brittle material, it's even smaller. Under such small strain considerations or infinitesimal deformation considerations, what we can say is that all the types of stresses are the same. So, for infinitesimal deformation, right, or deformation under the consideration of infinitesimal strain, we can say that all the stress measures are the same. Okay. So, in definition we are saying that F, which is equals to the I plus the gradient of U, which we can say that Fij equals to del Ij plus del Ui by del Xj. If this term is less than 1, is infinitesimal, and Fij is almost equals to del Ij, then the Jacobian, which is the determinant of Fij, will be approximately equals to 1. Okay, so Jacobian becomes almost equals to 1. Our deformation gradients are almost equals to 1. So with that definition, sigma ij will be equals to Sij, will be equals to tau ij, will be equals to sigma ij. So all the stress definitions become equal, and this is an important point to realize, because for small deformation we do not care about what kind of stress definition we are using. Again, just like the strain, stress definitions are not dependent upon their difference in derivations are not dependent because they are different stresses, rather it's the frame of reference that you are taking is different. So for small deformation, we can say that since the body is not deformed at all, initial state is very close to the final state, we can consider all types of stress states as same or similar. Okay, so we will use this definition mostly when we will be modeling different solid mechanics problem like membranes or plates likewise. Principal stress and principal directions most of you would know. So what is principal stress? So principal stress mathematically is the or are the, so if you take stress S, are the eigenvalues of the stress tensor, and the eigenvectors represent the principal direction. Okay. In some books you would find, especially say if you are looking at the Alan Bauer's book that we typically follow, principal stress and principal directions, principal stress is given by the left eigenvalue. There are two types of eigenvalues that can exist. One is which is multiplied with the left hand side of the matrix, and one is multiplied with the right hand side of the matrix. Since the Cauchy stress tensor, and in our case for the infinitesimal strain where all the stress tensors are equivalent, Cauchy stress tensor is symmetric, and a symmetric tensor will have the same left and right eigenvalues. So, and the eigenvectors are orthogonal to each other. So, with these properties we can define our principal stress, Okay, so let's make a drawing. All right, E1, E2, E3. Then this is sigma 1 along 1, sigma 2 along 2, and sigma 3 along 3. Okay, so our principal stress by definition, sigma star along n of k along any k direction will be equals to nj sigma of jk. Okay, so this is our principal stress. Okay. So there are three stresses. How do we find the principal stress? You find just like you would find any eigenvalue or eigenvector. Let me write down that eigenvectors are orthogonal. So we can see that they are orthogonal or 90 degree to each other. Orthogonal because our Cauchy stress tensor is symmetric. Okay. We are getting three values of sigma star. So, sigma star of 1 is greater than sigma star of 2 is always greater than sigma star of 3. That is by definition. So, it is useful, it is not required from a mathematical perspective, but it is useful to know which is the direction of the maximum stress, because this is useful to design for damage. So, if you want to prevent damage in a body, you can use this definition of the principal stress, that along the first principal direction the stress is the maximum, and along the third principal direction the stress is the minimum. Again, 1 does not mean along E1 or X1 or X direction, right? It can be any direction or any plane, but along the first direction you will have the maximum stress, then the second, and then the third. So, if you design your body to be strong along the direction of the primary principal stress or the principal stress 1, then your body will be safe to design. Okay. The maximum shear stress. So, the maximum shear stress acts on the shear plane, which is 45 degrees to M1 and M3. Okay. Our tau max is 1 by 2 of sigma star 1 minus sigma star 3. So, that is our maximum shear stress. If the body would fail under shear, then we use a maximum shear stress. There are a couple of definitions that we come up. One is called the hydrostatic stress. The hydrostatic stress sigma h is 1/3 the trace of our sigma tensor, that is sigma kk by 3. The second one is called the deviatoric stress. It is given by sigma dash ij, which is equals to sigma ij minus del ij into sigma h, right. And then we will have our von Mises stress, which is given by sigma Vm, which is square root of 3 by 2 sigma dash ij sigma dash ij. Okay. So, we have a vector collapse, a tensor collapse. So, a double dot product between our two stress tensors, two deviatoric stress tensors into 3 by 2, and square root of that will give us the von Mises stress. So, each of the stress has some physical significance. The hydrostatic stress is also called the pressure. Exerts a stress state to change the volume while preserving the shape. the deviatory component exerts a stress state rather, to change the shape, that is distort the shape, while preserving the volume. The von Mises can be considered as an uniaxial equivalent of a multiaxial stress state. Right, and it is used in some failure criteria, not all failure criteria, but there is certain failure criteria. Okay. So, sigma h is therefore in terms of our principal stress, sigma h is 1 by 3, sigma star 1 plus sigma star 2 plus sigma star 3. Our von Mises stress is square root 1 by 2 sigma star 1 minus sigma star 2 square, sigma 1 minus sigma 3 square, sigma 2 minus sigma 3 square. This is our von Mises stress. So, these are our stress definitions. These two stresses, they are the invariants of the Cauchy's stress tensor. So, a tensor that is a 3 by 3 can have 3 invariants. So, these are the invariants. The last one will be the determinant of J, that will give us the volumetric effects. So, sigma h Vm, and then there will be one more, and these are the invariants for our given system. Okay. So, we will start with the force equilibrium for today's lecture, and we will finish it up and go to the constitutive relation in the next lecture, right. So, what is force equilibrium? So, consider a solid that is deformed under external load or forces by the conservation of linear momentum. Our equation becomes del sigma j by del xj plus rho bi equals to rho ai. You can also say that the divergence of the sigma plus rho v vector equals to rho a vector. This is our force definition, right. What is this A of I? That is del squared u of I by del t square. So, it is related to our deformation. Likewise, this is del squared u vector by del t square. Okay. If the body is static, that is, it is not moving, and there is no body force, in that case the divergence of the stress tensor is equals to 0, that is del sigma ij by del xj is equals to 0. Okay. So, this is the condition that we will take for our body, which is under static equilibrium. It is not displacing, so all the forces are balanced out, there is no net acceleration and there is no net body force, right. We will use this quite often when we will talk about membranes and deformed shape. So, we will do the derivation for this in the next lecture. We will also see how the angular momentum affects. From that, we will go into constitutive relations relating stress to strain, and take up some examples of plane stress and plane strain and conditions. So I would like to thank you for listening to today's lecture, and we will meet in the next lecture. Thank you.